right, everybody, hello, and welcome to our lecture on correlation, co-relationships. This is an exciting topic to cover to me because correlation is one of the most chronically misused words in all of statistics, and I'm sure you're familiar with this word to some degree. What does it mean for there to be a co-relationship or a correlation between two variables? It might be a little bit more specific than you had originally thought. So we're going to go ahead and talk about correlations conceptually, and then we're going to talk about how we calculate correlations and fit them into a hypothesis test, where we use probability in the hypothesis testing procedure that we've been using insofar in the class. So when do we run correlations? We are interested in running correlations when we want to know if two variables are related. So it's a little bit redundant, right? A correlation is a co-relationship, looking for when two variables have a relationship. But we're looking at a specific type of relationship with correlations. We're looking at a coinciding increase and or decrease in a particular measure. So we might ask ourselves, does one variable increase as the other increases? For example, we might hope that as we increase our skills, we also increase our income, right? That's the general idea of getting higher education and skilled practice or trade practice. But we can also ask if one variable decreases as the other increases. For example, maybe as our nutrition increases, our health problems decrease. This is what we would also hope, right, from having, say, a healthy diet. So what do correlations tell us really? It tells us the relationship between two variables, and we'll see how correlation is reported. It tells us something specific about how strongly two variables are related. We measure it with something called the correlation coefficient. That's what we will be calculating. It's called the little letter R, or the Pearson's correlation. I'm going to let you go ahead and read this comic on your own time, but something you might have heard before, and that will be reiterated here, is that correlation does not imply causation. Correlation is somewhere in between a descriptive statistic and an inferential statistic. We're going to make it into an inferential statistic by doing a hypothesis test and using a p-value so we can make a prediction about, say, maybe another case in which we're looking at the same two variables. But this is not an experiment. We're not manipulating one thing and then observing an outcome. So this goes all the way back to our research design, our research methods lecture. Correlation just observes how two variables act together, but not how one influences the other. So this comic is kind of pointing to that, right? The cause in correlations is unable to be determined, even if we wanted to. So what I'm going to show you now is the correlation formula. So I will say, don't panic when you see this. It looks pretty bad, but it's not as bad as it looks, okay, I promise you. We're doing sort of a callback to when we worked on variance. We're going to be calculating correlation coefficients using a table. So we're calculating R, a lowercase r here. We call it Pearson's R. And then we have two variables. We have an x variable and a y variable. So if we remember all the way back to our different types of variables, we have independent and dependent variables. Independent variables are set up as predictors, and y variables are set up as outcomes. Again, we'll talk about why this isn't as practical of language to use with a correlation, but no less we have two variables that we're going to take a look at. We'll call them x and y. And another major consideration is that correlations can only be run on variables with equal interval data. So interval or ratio data, scale, continuous data, that's what we need. We say can't run a relationship between gender and some measure we're interested in because gender is not continuous or equal interval, right? It's categorical or nominal, much like we were working with last time with our chi-squared test. So we need to be mindful of that, and that's really the root of why correlation is such a misused word. People use the wrong types of data to describe relationships with data. So we can write hypotheses for correlations, which we will do. We're going to run a hypothesis test for our various examples here. So here we have it. We have kind of a new value here, a letter, whatever we want to call it. It's a Greek letter. Rho, spelled R-H-O, rho. It looks like a P, which of course just adds to the confusion as we use P for probability. That is not what this is here. This is rho, so spelled R-H-O. This is a lowercase rho. And this is going to be our population equivalent of a correlation. So for our hypotheses here, we'll basically be saying there's either no relationship present between the two variables that we're investigating, or there is a relationship present between the two variables we are investigating. All right, so either P or rho, oh, excuse me, oh my gosh, I just commit what I was just saying to not commit. Rho equal to 0 means that there's no relationship between the two variables. Rho not equaling 0 or being far from 0 and being statistically significant. Of course, we have some other things to consider when it comes to statistical significance. That is when we would consider our alternative hypothesis supported and that there is some type of significant relationship going on between our two variables. So something very nice about correlation is it'll come out between -1 and +1. Okay, always, all right? If you are calculating a correlation, you get something that is outside of the range of -1 and +1, that means something is wrong. That means something is fishy. But here we have a sort of depiction of how those different values indicate different relationships in data. So starting in the middle of this figure here, we have 0 correlation, or correlation of 0. Meaning that there's no relationship between the two variables in question. Let's say that we're interested in the correlationship between, what would we want to talk about? Maybe we want to talk about SAT scores or standardized testing scores and college performance, all right? Say we're measuring those two variables. If there's no relationship, it means that exactly that there's no relationship between the two, right? That standardized test performance doesn't indicate performance in college. However, if we found a positive relationship, right, maybe as scores increased on standardized tests, we also saw an increase in individuals in their college performance. Well, then we could say that there's a strong positive relationship between those two variables. So if you take a look at the left side of this figure, we have a few different labels, all right? So we have positive correlations and negative correlations. Positive means that we have a positive sign in front of it. Negative means we have a negative sign in front of it. So in addition to positive or negative, we can also describe correlations in terms of their strength, right? So the closer we get to +1 or -1, the stronger the correlation is. The closer we get to 0, the weaker it is, and we can call anything sort of in between a moderate correlation. So there are a lot of different breakdowns about how to generally describe these. What we'll move forward saying is anything above about 0.7 is considered to be quite strong. Anything beneath about 0.4 is considered to be quite weak. Anything in between would be considered a moderate correlation. So here we have it. We also have shape of distribution of data here. So notice that the positive correlation looks like a sort of upward trend. The trend of the data is moving upwards. It means that we're moving up on both the x and the y axis. That's why we call it a positive trend, because we're moving up on x and on y. Negative correlations are a little bit different. We're moving up on one variable. So if you take a look at this, notice that the x-axis is increasing as the y-axis decreases. All right, so maybe we have health problems and nutrition, right? Nutrition on the x-axis, health problems on the y. As we increase nutrition, we decrease number of health problems. So this is the general idea that we have these descriptors that are helpful. So in addition to determining if a correlation is significant, we can describe the general shape, trend of the data, right, or the strength of the particular relationship. So we'll look at just a couple cases of this, all right? Here's a positive correlation, right, a scatter plot, video games and alcohol consumption, all right, as one goes up, as does the other. This one was interesting to me. I thought that maybe video gamers might have another substance of choice, maybe not alcohol, but here we have a trend here, a positive one, and a negative one, a negative correlation. So we have exam scores and average hours of video games per week. All right, as hours go up, exam scores go down generally, right? So just take a look at the kind of general trend here. I didn't report statistics along with this, just so we can get an idea about how shape of distribution can immediately inform us of at least some part of the relationship here. All right, and then just for laughs, I have one of these. Correlation seems to have the most comics and jokes associated with it, so please just spare me and read them and try to laugh at them. But here we are. All right, won't spend too much time on this one. All right, so we're going to talk about one other aspect of correlations. This is something that we will not calculate ourselves, but that we will do in our lab portion of correlations, which is using what we call a partial correlation. A partial correlation measures the strength of dependence between a pair of variables that is not accounted for by the change in response to variation based on a subset of other variables. So that's very long, okay? But what it's basically saying is that when you look at a correlation, you're looking at the relationship between two variables. It's very, very unlikely, and very, very, very unlikely, I mean, to assume that the two variables that you're looking at are the only ones that influence each other. All right, so if you take a look here, if you want to look at the relationship between diet and weight loss, exercise probably is poking its head into that relationship too, and vice versa, right? Exercise and weight loss, diet will be contributing to that as well. So we have lots of cases of this. One correlation I like to talk about while we're still kind of on the video game topic is that violent video games cause aggression in children. You've maybe heard this before. So the first big issue is that video games don't cause aggression, right? They might be linked to or related to, but we can't say that it causes aggression because we're talking about a correlation or a co-relationship. So you've maybe heard this, that violent video games cause aggression in kids. Well, in order to do such a thing, we would need to run an experiment where we would need to put some kids into a group where they're exposed to violent media and some where they are not, and then test over time how aggressive those children are. And while that seems like a good idea for science, that's not a great idea for parents, right? Who would want to sign their child up to be exposed to violent media? Which is ironic considering that some kids are exposed to it anyway, but I will digress. The idea is that people will state that correlations exist, that co-relationships exist, when they really don't have the grounds to do so. And even if a correlation does exist, we need to assess it using a sort of critical eye or using some type of scientific knowledge or background to assess the meaningfulness of a claim. So we're going to look at a couple of funny correlations, some silly co-relationships, to see why correlations are inherently sort of problematic and why we need to be careful when we're talking about and interpreting correlations. So here we have a relationship between the divorce rate in Maine and per capita consumption of margarine, okay? And if we take a look here, albeit it's a little bit small, we have a correlation or an R value that's equal to 0.99, almost a perfect co-relationship, meaning that as one of these decreases, the other decreases at almost the exact same rate. So this might beg the question, right? Are these two things really related to each other? Well, if we had some scientific background in this, right, and we knew that some relationship was already present between these two things, we might be able to make a case for this. But however, we don't really have a case for this, right, unless you want to get creative. And when I do live classes, I like to get some theories about why this relationship might exist. But this is silly, right? This is funny. We can say, all right, of course, there's no true relationship between consumption of margarine and divorce rate. Those are two variables that are not exactly related by our current understanding. Here's another silly one. This one's, pardon the graph, it's another reason I include it because this is just a ridiculous depiction of anything. But it's looking at the relationship between ice cream sales and murders. This is a very common example for explaining what we call spurious correlations, which are basically meaningless correlations. This or ice cream sales and shark attacks. And then what we might want to do is think about, okay, what we know about partial correlations and what we know about correlations in general is that other variables will often contribute to the outcomes we see. So we might think to ourselves, what else would be contributing here? And it's right on the graph, right? Maybe the time of year. You've maybe heard this before, that more violent crimes happen in the summer months because of better weather. So that's very kind of bleak and morbid. But that's why we see this relationship as well, right? Murders rise as a result of temperature. Ice cream sales rise as a result of temperature. Doesn't mean they have anything to do with each other, just means that they are rising simultaneously. And we can say that they have a strong co-relationship because they do, but is it meaningful? Not really, all right? Unless we're getting creative or unless there's something we're simply not understanding at this point in time. All right, here's just another strange one. All right, so total U.S. highway fatality rate and fresh lemons imported to the USA from Mexico. All right, an R value of 0.97, again, almost perfect, almost perfect. This was published by an U.S. Department of Agriculture. So this is a real statistic, right? It's not to say that this statistic is fake or false, but we want to question if it's meaningful, right? Or if the relationship exists because these two variables are in fact related or because something else is driving this in particular. So we could think about why. So the ones we've talked about insofar are a little bit silly, right? We can kind of say, you know, no harm, no foul, right? It's just kind of strange statistics being reported that most people probably aren't putting too much of their hearts into. But this one is particularly sensitive. This is about autism diagnoses rising. If you're not familiar, autism diagnoses have been on a steady rise for the past few decades. And there's some question about if autism is actually becoming more prevalent or if it's simply being diagnosed more. However, scientists are still interested in what causes autism or what things contribute to autism. So this was a study published, I believe this was published in 2010. It's a little bit older now, but it created quite the stir because it compared autism diagnoses and organic food sales, right? And it shows a near perfect co-relationship. So as a scientist, you might look at this and say, hey, well, maybe these things both rose together, even though they're not related, right? Autism diagnoses maybe rose due to a greater availability of services and schools in which you could get diagnosed. And maybe organic food sales rose for a similar reason, that they're just simply more accessible to people. But that's not what happened when this study hit the ground. What happened was a layman population, a population of people who are not scientists, took this information and ran with it and said that organic foods cause autism. And I don't think I need to remind us of a more recent example with vaccines. A relationship between two things doesn't mean a cause and effect relationship. And in fact, in cases like this, it often means really nothing at all. It just means a sort of happenstance or time. Time is often that third variable that's not being accounted for. So that's included here on this graph. But again, we can talk about silly correlations all day long, but correlations are being reported all the time for better or worse, and it's good for any single person to have an understanding of what a correlation is so that we don't put more meaning into it than is due. Correlations often serve as a basis for further investigation, as much of science and much of statistics already is. But if we see a very strong relationship between two variables, the next step would be to say, do experiments on those variables, because correlations are not experiments. They're just observing how two variables are reacting, interacting with each other. All right, and the last piece of my correlations rant, okay, is that correlations are very diverse in presentation. So we're actually going to learn how to do small scatter plots so we can start to take a look at the shape of correlations. But I really like this image because this shows how many different, we have 16 different scatter plots or correlationships. All of these different graphs have the exact same correlation coefficient. All right, the exact same correlation coefficient of 0.5. a moderate correlation. But look how different each of these are, all right? We see clustered data, clustered in different areas on these plots. We see the third one down on the left column, and we see a quadratic relationship that's not being seen. We see other kind of trends in data, like right to the right of that, kind of a squiggly line that is not a linear relationship at all. And then down in the bottom row, we see things like groups of data, right? Correlations are not built to handle groups of data by themselves. You can run separate correlations to assess groups, but it's not built into the statistic. So if you dump data into, say, a correlational analysis, you can get two groups, and then that analysis might be better served by, say, a t-test, because now we're t-test experts, aren't we? Okay, so that's it for the conceptual overview of correlations. So now let's go ahead and try to do them. All right, let's give them a shot. All right. Let's see, what do we want to begin with? Let's start with a simple correlation. Let's start with the relationship between sleep and mood. Okay, are we in a better mood when we sleep more? There's kind of diminishing returns with this, I think. I think if you sleep too much, your mood can be kind of negatively impacted. But we're just going to talk about the relationship between sleep and mood. We're going to have sleep scores on a scale of 1 to 5. We're going to have mood scores on a scale of 1 to 6. And I'll go ahead and give you some data here. So we're going to talk about a few different things about just how this data is being presented in the first place. So we have, these are scores for sleep, right? 1 through 5. 1 meaning low sleep quality, 5 meaning great sleep quality. Okay, and then for mood, we have some scores. So before I move forward here, I'm going to stop and say something specific here. All right, we're going to carry this with us for the rest of correlations. When we have two scores reported like this, these scores go together. So we're talking about one person's sleep and their mood. So one person says, my sleep quality is a 2, my mood is a 4. All right, so I'm going to go ahead and continue this for each of these. And we'll go ahead and set this up in a way that might make this a little bit more obvious. Okay, 3, 6, 5, and 5. Okay, so here we have it. So each of these are sets of data. So the first thing we'll address is, what would n be in this case then? Well, n would be equal to how many pairs of data we have. All right, so we have 7 pairs of data. Our n would be equal to 7. Okay, so let's go ahead and I'm going to invert these. And this is sort of how I'll be writing these out here forth, is putting these into columns to make it a little easier to digest. All right, so we have 2, 1, 3, 2, 4, 5, 3. All right, we're a little askew there, but that's okay. 4, 3, 4, 3, 6, 5, 5. Okay, so we have our data here. And now what do we want to do with it? All right, well, let's start by thinking of a hypothesis. What's our prediction about this data? All right, what is our prediction? I'm actually going to move my n. Let's move n. Oh goodness, it wants me to keep erasing. All right, so let's move n. Oh goodness. All right, let's move n over here. All right, n equal to 7. And let's get hypotheses over here. All right, so hypotheses for correlations are really quite simple. We're always just either going to predict that there is a relationship or there isn't, all right? So the null would be that there is not, that the relationship will be close to 0. The alternative is that there is a relationship, that we're going to find something significantly different than 0. All right, let's go ahead and test this relationship at an alpha of 0.05, or at our old trusty alpha value of 0.05. All right, so we have x and y. And now let's go ahead, I'm going to give us a separate slide here let's think about that big formula that we were given in the slides, all right? So R is equal to N. We just determined what N is. N times the sum of the product of X and Y, product meaning what you get when you multiply them, all right, minus the sum of X times the sum of Y all over, all right, all over a very big square root sign, all right, big square root sign, where we have N times the sum of X squared minus the sum of X squared, all right, just a slightly different order here. And then we do the same thing for the Y variable. Okay. So again, this formula is a little intimidating to look at, right? There are kind of a lot of moving parts here. But what can we do to simplify this? Well, we can start by just getting these values here, all right? What's the sum of X and the sum of Y? That's already a big portion of this particular formula. So if we hop back here, let's go ahead and get the sum of X and the sum of Y. So we're just summing up all of these values. If we sum up all these X values, we get 20. If we sum up all these Y values, we get, well, not 20 again, we get 30. All right, so then if we hop back over to our formula here, so we have this, and this out of the way, what else do we need? Well, we need the sum of X and Y, we need the X's squared and the Y's squared. So let's go ahead and get those, all right? So we need, let's get another color. All right, we need the product of X and Y, we need the X's squared, and we need the Y's squared. So when we're talking about X and Y, what we mean is multiplying these values. Remember, we're treating these values as a sort of set. So we multiply these two values together. So 2 times 4 gives us 8. 3 times 1 gives us 3. 3 times 4 gives us 12. And we move down the line this way. All right, what else do we have? 24, 25, 15. All right, let's get all the X values squared. So we're just going in order, right? So we're taking 2 squared, 1 squared, 3 squared, just going down the line. So we get 4, 1, 9, 4, 16, 25, and 9. And we do the same for Y, right? So we take 4 squared, 3 squared. We just go ahead and move down the list. So we have 16, 9, 16, 9, 36, 25, and 25. All right, we want to get sum scores for these too because the formula calls for the sum of these values. All right, so if we sum these up, we should get something like this: 93, 68, and 136. All right, so let's go ahead and plug this into our formula, but before we do, let's get a cutoff score, because remember, this is just like our other hypothesis tests. So our first step is to grab our null and alternative hypotheses. The second is to get a cutoff score. All right, so what do we need to find our cutoff score? We need degrees of freedom and we need N. All right, so we have N and we need our alpha value. So we'll have something like degrees of freedom is equal to N minus 2. All right, N minus 2. So this is where this is a little tricky because remember, N is already a bit strange, but remember that X and Y are treated as a set, all right? So this is person 1's responses, 2, 3, all right, sets of responses. But we do subtract 1 from each of our separate variables to give freedom to vary for each of the variables. So in this case, we'd be taking 7 minus 2. We have 5 degrees of freedom. So let's go ahead and hop over to our R table. Let's see, I have to have one lying around. Where do we have one? All right. Oh, okay. All right, we have an R table here. Let me get this out of the way. All right, an R table here. So we're looking at an alpha level of 0.05, and we're looking at degrees of freedom of 5. So we're going down to the 5th row in the 0.05 column, and we find a value like 0.755. 0.755. So our R critical R critical is equal to plus or minus 0.755. So this is much like the other hypothesis tests that we've done in which we're interested in magnitude of the relationship. So this could be a positive relationship, it could be a negative relationship, but no less we need it to exceed 0.755 in order for it to be significant. All right, so our hypothesis testing steps, the first step is hypotheses, the second is cutoff scores, the third is calculating. So let's go ahead and start moving all of these values over to calculate. So the first piece of the formula is n times the sum of x and y, which is 93. And then we need to multiply the sum of x and the sum of y together. So I'll go ahead and do that here. So r is equal to 7 times 93 minus 20 times 30. All right, that's our numerator. And then in the denominator, we have an n of 7 times the sum of the x's squared. Well, that's this value right here, which is 68. 68. All right, and we're subtracting the sum of x, which is the same as this value here. So we're taking 20 squared. All right, we'll do the same for y. We'll take 7 times the sum of y squared, which is 136, and subtract the y's squared. All right, so if we do a little bit of math here, if I do a little bit of math in the numerator and a little bit of math in the denominator, we can simplify this quite a bit. All right, so 476 minus 400. Remember, we are just following order of operations, so I'm starting with the exponents and the parentheses underneath the square root sign. So that's where we will begin, is with the exponents, and work our way out to square rooting the denominator. We can treat the numerator and denominator separately, and we divide at the end. So then we have 952 minus 900. All right, sorry for the crunchedness of it all here. So we have 51 all over the square root of 76 and 52, right? Those different scores underneath. So we have 51 over the square root of 39. 52 equals, just doing this out at every step, so you can go ahead and try this for yourself and make sure you're getting the same values as me. 8, 6, 4, 9. All right, all the way to, let's get another color to signify our R value. We end up with an R value of positive, right? It's positive because there's no negative sign. It's good to get in the habit of just marking correlations as positive or negative. Correlation of 0.811. So before we even move forward with this and go back to check our hypothesis test, let's just describe this relationship. All right, this is what we would call a strong positive correlation. All right, it's strong, it's greater than about 0.7, and it's positive, meaning that there's an upward trend to the data. So if we go ahead and think about our cutoff score that we established, right, we were looking for something greater in magnitude than 0.755. Right, 0.755, all right, and then we have our critical region over here. Did we fall into that critical region? I think we did, right? We'd be somewhere over here with our 0.811, and we would go ahead and reject the null hypothesis. It seems that there is a relationship between sleep and mood. And not only is there a relationship, but there is a strong and positive one, which is great news, all right? But we already knew that, right? We knew that sleep and mood were linked. But now let's go ahead and think about how we could visualize this data, all right? Here's an X and Y axis. So just like we used to do with histograms, we're going to have an X and a Y axis using the X and Y variables that were given. So in this case, the X variable was sleep, and the Y variable was mood. All right. So sleep, we have 1, 2, 3, 4, 5. People rated their sleep on a scale of 1 to 5. And then mood was on a scale of 1, 2, 3, 4, 5, 6. So we're going from small mood to a big mood up here, all right, for 6. right, so let's go ahead and give this a try. How do we do a scatter plot? Well, our data, all right, we should think of as coordinates, right? So this first person had a 2 for their sleep score and 4 for their mood. So we'll go to our graph and we'll go to the 2 for sleep score and up to 4 for mood. Our next person had a 1 on sleep and 3 on mood. We'll go ahead and put them in here. We had 3 and 4. We had 2 and 3. We had 4 and 6. We had 5 and 5. All right, getting a little crunched here. 5 and 5, and then 3 and 5. Right, so we can sort of see that we have an upward trend here. All right, it's not perfect, but it can kind of help our eye to just see, right, what general direction is this data going in. All right, it's going up, right? So something else to mention while we're at it is that this is not a lot of data that we are working with. In reality, we're often working with much larger data sets. We would not necessarily run a correlation with this little data. However, I'm not going to have us calculate by hand anything that is a little too crazy. All right, so let's go ahead and try one more. Let's give another one a try. Let's look at an X variable. Let's look at hours a day outdoors. And let's see how that impacts maybe, or its relationship to anxiety, right? Do we think there's maybe a relationship here? I would say maybe, right? Being outdoors is nice, can help calm the mind. Let's go ahead and get some data in here. In fact, I'll just go ahead and throw it into our table. No need to write it down twice. All right, so for X and for Y, let's scoot this over, X and Y. So for hours a day outdoors, we have data as follows. Right, because some people work outside, some people are outside for their hobbies, some people don't go outside very much at all right? So we have sort of a range of values here. And then for Y, for anxiety, we have this on a 1 to 10 scale, so we have values here. Okay. So before we move forward, let's get our hypotheses in place here. So the null hypothesis is that there is no relationship, all right? And you could write this out verbally as saying that there is no relationship between hours outside per day and anxiety. And the alternative is that there is a relationship between hours outside per day and anxiety. And let's go ahead and test this at an alpha of 0.01. Let's go for a more restrictive alpha value here. All right, so let's go ahead and think about the formula again, our big long formula. So R is equal to N times the sum of X and Y minus sum of X and the sum of Y. We're going to put that all over the big square root sign. We take N times the sum of the X's squared minus the sum of the X's squared in a different order. All right, then the sum of the Y squared. It's almost exhausting just to even write it, but just stay strong, you know. Remember that once you get your table going, you're halfway done, right? Most of the work is done before we even get to the formula. So let's go ahead and start to work through this. But first, let's get our critical value. All right, so we need degrees of freedom. And what is our N here? Our N is equal to 1, 2, 3, 4, 5, 6, 7, 8. Our N is equal to 8. Remember, that is because we are treating each of these as sets. So this is one data point, 1, 2, 3. You get the idea, right? It's the same person reporting two variables. So degrees of freedom is equal to N minus 2. We have 8 minus 2, so we have 6 degrees of freedom and an alpha of 0.01. Let's take a look at our table. If we go down to the row that indicates 6 degrees of freedom, and we go over to the 0.01 column, we get an R critical value of 0.834. All right, so R critical equal to 0.834. All right, 0.834, and of course plus and minus, because we don't have a specific prediction about if there's going to be a positive or a negative relationship here. We are just looking for any type of relationship. Okay, so our critical is done. Let's go ahead and start calculating here. Let's start by just getting our sum of x and our sum of y. Our sum of x is equal to 36. Our sum of y is equal to 44. All right, so let's go ahead and get x and y. We're multiplying the x and y values together. So we have 8, we have 16, 30, 24, 21, 21, 20, and 18. All right, if we sum these up, let's sum the x's and y's, we get 158. And then we need each of our x values squared, each of our y values squared, so we can sum those up as well. So we have 1, 64, 25, 36, 49, 9, 16, and 4. Sum of x's squared gives us something like 204. Then the y squared, we have 64, 4, 36, 16, 9, 49, 25, and 81. We have our sum of our y's squared equal to 284. Okay, so again, not a whole lot of math here to really fill out this entire formula. So let's go ahead and start moving each of these values over. All right, so if I plug everything in, we should have a formula that looks something like this. All right, let's put it all over. Big square root sign. So I'm doing brackets here because we have parentheses within brackets. Just in case you're wondering what that is, it might be a while since you've seen such a thing, but it just basically means that we have embedded parentheses here. Okay, so there we have it. If we take this one step further, we get something like this. And of course, do this math alongside me. All right, it's one thing to just watch this be done, and it's another to make sure that you can get the same types of values as me. All right, so 1632 minus 1296, a little bit hard to see. And then we have something like 2272 minus 1936. All right, so a little hard to see, but I'll show you in this next step what we boil down to here. So we end up with negative 320 on top. Ooh, a negative. What does that mean? That means that we probably have a negative relationship coming our way, right? This is going to make our R value negative. And we're putting this all over the square root of 336 times 336. Isn't that odd? The same value, but that's okay. So we got negative 320 all over the square root of a big number, 112896. However, since there were two of the same value going in here, we know that the denominator is 336. All right, 336. And what do we get? We get negative 0.95. All right, that's our final R value. So how do we describe this one? Well, it's pretty strong, and it's negative. All right, so this is a strong negative correlation. So how strong is it? Is it strong enough, right, to surpass our critical value? And what was our critical value? It was something like 0.834. 834. All right, so it's somewhere, well, for the sake of argument, we'll put it on the right side, the negative side. But remember, it doesn't matter because we're just talking magnitude anyway. But still helps the brain to think of it this way, right? So our negative 0.95 is greater in magnitude than our cutoff score. So this is in fact significant, and we would reject the null. So if we hop back over here, we would reject the null, reject the null. And we would have some evidence that there is a relationship between these two things. All right, so let's go ahead and plot this as well. Let's get ourselves a graph going here. Let's plot Ah, that's not very good. Let's try and make it a little better. There we go. Not much better, but a little bit. So X is hours spent outside, and we have 1 through 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. All right, and then we have anxiety over here on a 1 through 10 scale. We had reported from 9, 8, 7, 6, 5, 4, 3, 2, 1. 1, 2, 3, 4, 5, 6, 7, 8. All right, there we have it. So now we're going to take a look at each of our sets of data. So the first person reported 1 hour outside per day and an anxiety level of 8. Then we have someone reporting 8 hours outside per day with an anxiety level of 2, 5 and 6, 6 and 4, 7 and 3, 3 and 7, 4 and 5, and lastly 2 and 9. All right, so we can see here that there is a general sort of downward trend. And one little trick I like to think about here is that to identify a negative correlation, it sort of looks like if you were to draw an N for negative, this is the direction of the line in a negative relationship. So that's a little way to help us remember. But with that, that concludes our introduction to correlation. So when we're working with correlations for this class, we want to be able to write out a hypothesis, a set of hypotheses that indicate either no relationship or a relationship between our two variables. We want to be able to find a cutoff score using degrees of freedom in our alpha level using the R table. And then we want to be able to calculate our correlation coefficient using this table method, describe the relationship, determine if it's significant, and plot it to give us a better idea of the shape of the distribution. So please be in touch if you have any questions on this topic.